So let's talk about another topic here, the brightness of stars and realization that stars weren't all the same brightness. Remember we talked about the HR diagram, and we said that on the HR diagram that you could have, for example, most stars were on the main sequence, but stars that were up here were the same temperature as stars down here, but they were brighter, and that meant they had to be bigger. And so they began to realize those stars got to be giant. We talked about sizes of stars in the previous lecture. Some stars are truly giant compared to the others. You can sort of estimate the size of a star by looking at the width of the spectral lines. Typically, the narrower the spectral lines, the brighter the star is, and the wider the spectral lines, the dimmer the star is. So this would be a bigger star, and then that'd be a smaller star. So you again look at the HR diagram. Remember that hotter is to the left, cooler is to the right, brighter is to the top, dimmer is to the bottom. So if you have a star that's up here, that star is exactly the same temperature as a star down here, but it's obviously vastly brighter, so it has to be vastly bigger. Well, this star over here is going to be the same brightness as that star, but it's much hotter, so it has to be much smaller. So what you get out of this is, on the HR diagram, the farther you go up to the upper right, the bigger the star is. And then conversely, the farther you go this way, the smaller the star. So if we imagine the sun and say the sun is one solar radius here, then as you go this way, you get bigger. As you go this way, you get smaller. Now, interesting to note, the main sequence doesn't line up exactly along that diagonal line. So as you go up the main sequence, you're actually getting some slightly bigger stars. Go down the main sequence, you're getting smaller stars. Now, this is a logarithmic thing, so that line is 10 times this. That's not 20 times. That's 10 times the previous one. So this line up here is 100 times that size. This one up here is not 200. It's 1,000 times, because it's 10 times this, which is 10 times that, which is 10 times that. So that's 1,000 times bigger. You go this way, this is a 1/10 the size of the sun, 1/100th the size of the sun, and 1/1000th the size of the sun. So stars that are way down here we call dwarf stars, white dwarfs if they're hot and white hot. Okay, these would start called red dwarfs because they are much smaller than the sun and they're reddish in color. And then these would be like red giants up here to the right because they're reddish and they're clearly giant type stars. And then really, really giant stars we call supergiants. Now the term dwarf, giant, and supergiant actually comes about from a classification system that was proposed by William Morgan and Philip Keenan. And so they developed a way of classifying stars based on luminosity. And they gave a Roman numeral to each luminosity class. So main sequence stars are technically considered dwarfs in their category, and so all main sequence stars are Roman numeral 5. And the giant stars are Roman numeral 3, and then the bright giants are Roman numeral 2, and then the less luminous, or the supergiants, then bright supergiants that are 1s, but they're like 1A or 1B. Any stars that are way down here would be subdwarfs. That'd be like the white dwarfs, be a subdwarf. So that would be the system. So imagine HR diagram. On the HR diagram, most stars are along here. That's the main sequence. Okay, so going this way is getting cooler. Going that way is hotter. Going this way is bigger. Going that way is smaller. Okay. Going that way is brighter. Going that way is dimmer. So, what I often will have students do is they'll look at this and they will then say, huh, okay, so on a table of data, you're going to be expected to figure out which stars are hotter, brighter, cooler, and dimmer. And so students often panic when they do that. And they say, well, how do I do that? For example, on this table of data, we have the spectral type and you got the Roman numerals here. And I would ask you, well, which star is hotter, which star is brighter, which star is bigger, which star is smaller, and so forth. And so students at first, they would kind of panic, but it's not that bad. Okay, so seriously, it's not that bad. So what you do though is you think about the HR diagram. So we have, for example, an M star right up here. We have an M star right there, and we have an M star right there. Well, these are all three M-type stars, so which one's bigger? Well, these are all main sequence stars. This is above the main sequence. So remember, you get off the main sequence. Again, kind of imagine you get the main sequence here, and we got the main sequence stars down here, and then we got one up here. Well, that up there, going this way from the main sequence, is getting bigger. So that means that this star is bigger than those other M-type stars. Okay, so next question would be, okay, so suppose that we have several stars here. We got this one right here, this one right here, that one, this one. Okay, so and let's see, that'll do. Those four stars right there are all giant stars. Okay, so which of those giant stars is biggest? So again, you got the HR diagram. All the giant stars are up here. Well, the M giants are over here. Okay, and the K and the G and the B. So farther that way is bigger. So that means that this would be the farthest one over, so that's going to be the farthest up. So that's going to be the biggest of the giant stars, and this is going to be the farthest over here, the smallest of the giant stars. So the B will be the smallest of the giant stars, the M will be the biggest of the giant stars. Again, that's looking at that HR diagram and imagining where these stars will fit on the HR diagram. So if I ask you for these stars, which one's brighter, dimmer, and so forth, that's a good way of doing it, is you can just imagine an HR diagram and where would that star fit on the HR diagram. Okay. Now, one thing I don't like about the Morgan-Keenan system is the names, because if you look at that diagram carefully, you notice that some of the giant stars are actually bigger than supergiants. For example, a red giant might be bigger than a blue supergiant. So, for example, this is going to be right here is a white hot. So way up near the top of the supergiants. So that star would be way over here, but this star is over here, and so that's really technically farther that way. So that star might actually be bigger than this one, even though this one is a giant, and Alpha Carini is actually a supergiant. So I don't really like the names that they assign to these things, but I wasn't the one that did it, and these are the standard sort of names that we use. But this is how you'd look at this chart and figure out size. And so that's a useful tool, be it by just looking at the spectral type, and we normally put the luminosity class with the spectral type. You can now find out even more about stars. Should also point out the spectrum also tells you something about the rotation rate of stars. That by looking at how the spectral lines are, you can also tell how fast the star's rotating. And stars that rotate a whole lot can act, because they're a big ball of gas, they can actually flatten out. The star Regulus is actually rotating so fast, it's almost tearing itself apart. Centrifugal force is pushing the edges out, so it's not even round, it's kind of oblong here. The sun rotates, once every few weeks, and so the sun actually looks kind of round compared to a star like Regulus. This also would change things. If you look at Regulus from one side versus the other side, you see more of it, and so it would actually look brighter from one side than from another.